Welcome friends. In this video, we will discuss about inner product spaces. You are familiar with the definition of vector space. In vector space, we combine vector and scalars. V is an abelian group, F is field, and when there are some additional condition such that for u comma v vectors and alpha comma beta scalars, first conditions alpha dot u plus v equal to u v alpha u plus alpha v, second condition alpha plus beta into v equal to alpha v plus beta v, third condition alpha times beta v equal to alpha into beta times v, and fourth condition 1 into v equal to v. If these conditions are satisfied, then it is called as a vector space. We know that in a vector spaces, if V is a vector space, then it is defined over the field, and the field is any field, it is an arbitrary field. Now we restrict ourselves to a field of real numbers or a field of complex numbers, and we impose conditions on a vector space. If we have a function whose domain set is a vector and whose range set is field, with the field is set of real number or set of complex number, such that then with four conditions, and that four conditions, with the four condition, first condition we denote this here new notation for this function as this in parenthesis u comma v. It is not an order pair. Remember, here we are defining a function. It is not an order pair, but it is a function where u comma v are the vectors. When this function satisfies four conditions, first condition is u comma v equal to v comma u, its conjugate. Here we have taken that the field, this inner product is defined over the vector space, and this inner product is a member of F. Here F is, we have taken a real number set or a complex number set, and we know that in complex number there are conjugates. If z is equal to x plus iy is a complex number, then its conjugate is x minus iy. Similarly, when the u comma v as a suppose the number of member of a field f, and then v comma u is also a member of field f, if we take its conjugate and when it equal to u comma v, this is the first condition of inner product space. And second condition, inner product of u with itself is greater than equal to 0. It is 0, u comma u equal to 0 if and only if u equal to 0. Third condition of inner product space is linear property alpha u plus beta v comma w equal to alpha times u comma w plus beta times v comma w. This is the third condition of inner product space. So when a vector space with these properties, it is called as a inner product space. Remember that we are defining a function over a vector space, and we are imposing some additional conditions over this field, over this vector space, and the inner product is nothing but a real number or a complex number. You are aware about the fact that if we consider V equal to n tuple vector space, that is, it is of the type, suppose alpha 1 comma alpha 2 dash 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 alpha n. This is a one member of f raised to n tuple vector space. Then this beta 1, beta 2, beta n, this is another member, where this alpha and beta are either real number or complex number. Alpha I comma beta I belongs to f. We have restricted to ourselves as real or a complex number. Now we define how we can how there will be inner product. Suppose that this is my vector u and this is my vector v. Then we define u comma v equal to inner product of u and v. Okay, so remember that this is not an order pair, but this is a function. We are defining the inner product between the two vectors, where u is a n tuple and v is also n tuple. It is of the type alpha 1 beta 1 bar plus alpha 2 beta 2 bar plus alpha n into beta n bar. Beta 1 may be complex number, may be real number. Okay, so there are two possibilities, but we have considered the possibility of complex number and we have defined it is like alpha 1 beta 1 bar plus alpha 2 beta 2 bar plus alpha n beta n bar. Then we can see that the inner product of v and u, by this is a definition. According to this definition, this v comma u equal to, this is beta 1 alpha 1 bar plus beta 2 alpha 2 bar plus beta n alpha n bar. Now let us take the conjugate of this inner product. V comma u bar equal to, v comma u bar equal to beta 1 alpha 1 bar, okay, plus beta 2 alpha 2 bar plus beta n alpha n bar, its conjugate. Now this is equal to beta 1 bar into alpha 1 bar its conjugate plus beta 2 bar alpha 2 bar its conjugate plus beta n bar alpha n bar its conjugate. So see that here z equal to x plus I and z bar, conjugate of z equal to x minus I bar. Now if we consider, if we take the conjugate's conjugate, that is here if we take z bar, this is equal to x plus iy. So this is a z. Hence alpha 1 double bar means conjugate's conjugate, we get the same number. So this is equal to alpha 1, we interchange this multiplication and we get that alpha 1 into beta 1 bar plus alpha 2 into beta 2 bar plus alpha n into beta n bar. Okay, now this is equal to same as inner product of u comma v. So first condition of inner product space is satisfied. Now see the second condition. If we take the inner product of u with itself, then this is equal to alpha 1 bar plus alpha 2 bar plus alpha n bar. Okay. Now when z equal to x plus iy, z bar equal to x minus iy, z into z bar equal to x square plus y square, and this is nothing but mod of z square. If it is a complex number, and when it is not a complex number, it is a real number, for example 3, then 3 bar is also equal to 3. So 3 into 3 equal to 3 square. In both this case we get here square. So this is equal to, by taking consideration of possibility of complex number, we write it as a mod of alpha 1 bar plus mod of alpha 2 bar plus mod of alpha n bar. alpha n bar, not a bar but mod of alpha n square. Okay, mod of alpha 1 square, mod of alpha 2 square plus mod of alpha n square, and you know that every square quantity is a positive. So, each term is a positive and hence it is greater than 0. Okay. Now, when it is equal to 0, if every alpha equal to 0, that is here alpha 1 must be equal to 0, alpha 2 must be equal to 0 and alpha n, all alpha n equal to 0, that is we get a 0 tupled element 0 0 0 0. So, this is 0 vector. Okay, 0 vectors means when this u equal to 0, therefore inner product of u comma u equal to 0 if and only if the u equal to 0. So, two conditions of inner product space stated here. What are that two conditions? These are the two conditions. Look at this. First one is u comma v equal to inner product of v comma u bar. Then second condition, u comma u greater than equal to 0 and it is equal to 0 if and only if u equal to 0. Third condition, linear property. So, we have proved the two conditions. Now, we prove the third conditions. Okay. So, let me make some space to prove the third condition. I am erasing these parts so that we get some space and we can prove the third property. So, it is enough. So, let us first calculate the value of alpha u plus beta v equal to, what is alpha? Alpha into u, u means alpha 1, alpha 2, alpha n. Alpha 1, alpha 2 and alpha n, alpha 2, alpha n plus beta into beta 1, beta 2, beta n. You know that how to add this n tuple element. We get the product element as alpha alpha 1 plus beta beta 1 comma alpha alpha 2 plus beta beta 2 dash 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 alpha alpha n plus beta beta n. Okay. Now, let us that w equal to, suppose my w equal to gamma 1, gamma 2 and gamma n. Then inner product of alpha u plus beta v comma w, this is equal to alpha alpha 1 plus beta beta 1 comma alpha alpha 2 plus beta beta 2 dash 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 alpha alpha n plus beta beta n comma the inner product of this with the another element, that is gamma 1, gamma 2 dash 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 gamma n. Now, apply the definition. According to our definition, this is equal to alpha alpha 1 plus beta beta 1 into gamma 1 plus alpha alpha 2 plus beta beta 2 into gamma 2 plus alpha alpha n plus beta beta n into gamma n. So, this is equal to alpha alpha 1 gamma 1 plus beta beta 1 into gamma 1 plus alpha alpha 2 gamma 2 plus beta beta 2 gamma 2 plus alpha alpha n gamma n plus beta beta n gamma n. Now we separate the terms of alphas and betas. Okay, so if we write separately alpha times alpha 1 gamma 1 plus alpha 2 gamma 2 plus alpha n gamma n plus beta into beta 1 gamma 1 plus beta 2 gamma 2 plus beta n gamma n, then you can it is a alpha 1 beta 1 bar. So we have to take here gamma 1 bar, gamma 2 bar, gamma n bar, and so that here gamma 1 bar, gamma 1 bar, gamma 2 bar, gamma 2 bar, gamma n bar, gamma n bar. Then here we get alpha 1 gamma 1 bar, alpha 2 gamma 2 bar, alpha n gamma n bar, beta 1 gamma 1 bar, beta 2 gamma 2 bar, and beta n gamma n bar. But this is equal to alpha into this is inner product of u comma w plus beta into this is inner product of v comma w. So third condition of inner product space is satisfied, and hence this vector space V, n-tupled vector space is an inner product space. Okay, now we see another example of inner product space. I hope you get the concept of inner product space. What is inner product space? Inner product space is defined over a vector space with three more conditions. That conditions are: first condition is inner product, we have defined a function inner product which is a member of F, and the member u comma v, it is a function, and if satisfies the first condition u comma v equal to conjugate of inner product of v comma u. Second one, I am going to write here once again two vectors, define two vectors here u comma v belongs to capital V, an element. So there is an element u comma v, it is called as inner product element of F, which satisfies first condition inner product of u comma v equal to conjugate of inner product of v comma u. Then second condition, what is the second condition? Second condition is inner product of u comma u is greater than 0. It is 0, u comma u equal to 0 if and only if u equal to 0. And third condition, that is linearity, the inner product is linear over it is alpha u plus beta v comma w equal to alpha times inner product of u comma w plus beta times inner product of v comma w. This is the third condition. If all these three conditions are satisfied, then the vector space is called as a inner product space. Now let us see one more example. One more example of inner product space, very simple example of inner product space. Suppose my vector space is R square. Here we have chosen a field of real numbers. Now we define inner product for this vector space u comma v equal to, here we consider this u equal to alpha 1 comma alpha 2 and v equal to beta 1 comma beta 2. Now we define it as alpha 1 into beta 1 minus alpha 1 into beta 2 minus alpha 2 into beta 1 plus 4 into alpha 2 into beta 2. Now here we can check that actually it is an inner product space. Okay, so for our convenience, we take suppose u equal to 1 comma 2 and v equal to 3 comma 4, and by the definition let us calculate here the inner product u comma v. U comma v equal to alpha 1 is 1 into beta 1 3 minus 1 into beta 2 4 minus alpha 2 2 into beta 1 3 plus 4 into 2 into 4. This is equal to 3 minus 4 minus 6 plus 32. This is equal to 35 minus 10 equal to 25. So, you can see that how we have defined the inner product space and how we get a real number. Now, we show that this inner product space satisfies all the properties of inner product space. Now, let us find u comma v. U comma v equal to, this is equal to by definition beta 1 alpha 1 minus beta 1 alpha 2 minus beta 2 alpha 1 plus 4 beta 2 into alpha 2. Now, take the conjugate of this number v comma u bar equal to, this is beta 1 alpha 1 bar minus beta 2 alpha 2 bar minus beta 2 alpha 1 bar plus 4 into beta 2 alpha 2 bar. Then you can see that the conjugate of 3 is 3. For real number it is the same number. So, here alpha and betas are real number, therefore, for this term the beta 1 bar and alpha 1 bar is again the same number. So, this is equal to beta 1 into alpha 1 minus beta 2 into alpha 2 minus beta 2 into alpha 1 plus 4 into beta 2 into alpha 2, and we know that the real numbers are commutative. So, we write this as, this is equal to alpha 1 beta 1 bar alpha 1 beta 1 minus, here we write this first term as alpha 1 into beta 2 second term minus alpha 2 into beta 2 plus 4 into alpha 2 into beta 2. Now, you can check that this is nothing but inner product u comma v. First condition is satisfied. Now, second condition u comma u, this is equal to alpha 1 minus alpha 1 into alpha 2 minus alpha 2 into alpha 1 plus 4 alpha 2 into alpha 2. This is alpha 1 square minus, this is same alpha 1 into alpha 2 minus alpha 2 into alpha 1. So, this is twice alpha 1 alpha 2 plus 4 alpha 2 square equal to alpha 1 square minus 2 times alpha 1 alpha 2 plus alpha 2 square plus 3 times alpha 2 square. We have divided into two parts. The first part is nothing but alpha 1 minus alpha 2 square plus 3 into alpha 2 square. Both are square term, so it is always greater than 0. Now, it is equal to 0 if and only if this is equal to 0 and this is equal to 0. That is, this u comma u equal to 0 if and only if alpha 1 equal to alpha 2 and second alpha 2 equal to 0. Alpha 2 equal to 0 means alpha 1 must be equal to 0. So, both when alpha 2 and alpha 1 are 0, we have u comma u equal to 0, but alpha 1 equal to 0, alpha 2 equal to 0 means u equal to 0 comma 0, that is 0 vector. Here both the conditions are satisfied, therefore, we prove the third conditions of inner product space. The third conditions of inner product space is alpha u plus beta v. Let us consider alpha, calculate alpha u plus beta v. Alpha u plus beta v equal to alpha 1 plus beta beta 1 comma alpha alpha 2 plus beta beta 2. This is inner product. This is an term vector alpha u plus beta v. Now alpha u plus beta v with w, where w we take w as gamma 1 comma gamma 2. Then here first vector of this is equal to alpha alpha 1 plus beta beta 1 into gamma 1. Alpha alpha 1 plus beta once again I am writing this alpha u plus beta v comma w equal to alpha alpha 1 plus beta beta 1 into gamma 1 minus first element alpha alpha 1 plus beta beta 1 into gamma 2 minus second element, the second element is alpha alpha 2 plus beta beta 2 into first element of gamma 1 plus 4 times alpha alpha 2 plus beta beta 2 into gamma 2. Now you can see that how to multiply this. You are all familiar with the multiplication. So here we get this multiplication as product of this. This is equal to, let us multiply, this is equal to alpha alpha 1 into gamma 1 plus beta beta 1 into gamma 1 minus alpha alpha 1 into gamma 2 minus beta beta 1 into gamma 2 minus alpha alpha 2 into gamma 1 minus beta beta 2 into gamma 1 plus 4 times alpha alpha 2 gamma 2 plus 4 times beta beta 2 into gamma 2. Now separating the terms of alphas and betas equal to alpha into alpha 1 into gamma 1 minus alpha 1 into gamma 2 minus alpha 2 into gamma 1 plus 4 alpha 2 gamma 2 plus beta into beta 1 gamma 1 minus beta 1 gamma 2 minus beta 2 gamma 1 and plus 4 into beta 2 gamma 2. The second, the parenthesis term, bracket term is nothing but inner product of u comma w plus beta into inner product of v comma w. So second condition is also satisfied, and hence this R2 is really a inner product space, or order tuple over the field of real number is inner product space. So we have seen two examples of inner product space. Now we see that this inner product is not linear over as a second variable. It is linear as first variable, but it is not linear as a second variable. Now if we take it as a u comma alpha v plus beta w, then by definition this is equal to alpha v plus beta w. We know how to distribute as a first variable, and therefore we should apply the property of the inner product space. By the first property we should take the complex conjugate. It is equal to complex conjugate, and this is equal to, here it is distributive, so this is equal to alpha into v comma u plus beta into w comma u. Okay, but this is equal to alpha bar v comma u bar plus beta bar w comma u bar. Okay, so this is equal to alpha bar, but by definition this is u comma v plus beta bar into u comma w. Here the alpha z and z bar both are different number. Therefore, alpha is not equal to alpha bar, beta is not equal to beta bar, and hence this is not linear as a second variable. Inner product is not linear as a second variable, it is linear as a first variable. Okay. So, friend, here we have seen what is meant by inner product space, what is meant by uh, inner product, how we can define the inner product, definition of inner product space, examples of inner product space. Okay, so let us stop here.